Hi everyone, I'm Yuanwei Lu from University of Science and Technology of China. My topic today is multipath transport for RDMA in data centers. This is a joint work with USTC, Microsoft Research, Hunan University, Huawei Technologies, and Microsoft Azure. So as we all know that remote direct memory access, aka RDMA, does kernel bypass, so it provides low and stable latency. And also it does transport hardware offloading, so it can provide high throughput with low CPU overhead. Currently, RDMA is deployed at scale in Microsoft data centers. Half of the traffic in online service of Microsoft data center is currently running RDMA traffic. However, the data center topologies, as we all know that FAT3, B-cube, VL2, those kind of topologies have lots of parallel paths between any pair of nodes. However, current RDMA remains a single path transport, and all the data belongs to one connection will flow over one physical path and using ECMP as the load balancing scheme. And we all know that ECMP will cause hotspots in network and leads to high latency and low throughput. Also, it is not so robust to failure. So in the TCP world, we have multipath TCP to solve all the problems of single path TCP. However, in the RDMA world, there is no such a counterpart. So our goal in this work is to seek how can we design a high-performance multipath transport for RDMA, and we name it MP-RDMA. So the RDMA environment is quite unique compared with the TCP environment. So we cannot adopt the multipath TCP solution directly to the RDMA world. The main uniqueness of the RDMA environment is that RDMA must be implemented in hardware. And hardware on-chip memory is very scarce, so it usually serves as a cache. So that means when one packet comes to the from send or receive packets to the network, so usually first it will request some states on the NIC. And when it cannot find states on the NIC, so cache miss will happen, then it will go to the host memory to access the states stored in the host memory. However, if frequent cache miss happens, then PCI bandwidth will become the bottleneck and will also lead to large and unstable latency. So further will result in poor performance for RDMA. So we have done an experiment in our testbed. As we can see that when the number of concurrent connection reach over 256, the RDMA throughput drops quickly. So this gives us the insight that MP-RDMA design should add as little hardware memory footprint as possible compared with existing single-path RDMA, so it can support the same number of concurrent connections in the on-chip memory, so the performance will not downgrade. This uniqueness of RDMA environment leads to several challenges, and we will talk about it one by one. So the first challenge is how to achieve congestion-aware traffic split without per-path states at NIC. So if we design a multipath transport, so the first thing we need to do is to conduct congestion-aware node balance and to distribute the traffic according to all the path conditions. So in the multipath TCP, it tracks the transmission and congestion states on every path to maintain per-path states, so it can do congestion-aware node distribution. However, if we adopt this approach, if MP-RDMA adopt this approach, 8 paths will require about 368 bytes at least. So it will lead to more frequent cache miss because currently the Rocky V2 implementation only stores about 248 bytes per connection on its NIC. So this give us the first challenge is how to achieve congestion-aware traffic split without per-path states at the NIC. So our solution is level multipath ACK clocking. So our insight is that we want to design a transport without per-path states. We use a window-based protocol with ACK clocking. So our algorithm basically runs as follows. So at the beginning, we will spread n packets randomly to n paths. And then we only maintain one congestion window for all the sending paths. And for each received ACK, if it is a ECN packet, then the congestion window will be decreased by half a segment. And if it is not an ECN packet, we will additively increase the congestion window. And for every returned ACK, we will clock out one packet to the path that ACK returns when the congestion window allows it to do so. So although we only use one congestion window for all the paths, as we can see, it can, in an example I will show next, that it will can do congestion-aware path distribution. So let's look at the example. So let's say that the initial congestion window is 6. So we will send out 6 packets to the 3 paths. And let's assume that the first path is congested, and it will receive ECN ACK. And when the first ECN ACK arrives, then the congestion window will decrease by half a segment, then it becomes 5.5. However, the in-flight packet is still 5 packets, so the available window is only half a packet, so it cannot clock out one packet to the path that ACK returns. And when the second ACK, ECN ACK returns, so the congestion window further will reduce by half a segment, and the in-flight currently is 4, and the available window becomes 1. So it can clock out one packet to the path that is congested. And for those paths that is not congested, it will send as much packets as the ACK returns. So as we can see in this example, although we only use one congestion window, we can conduct congestion-aware traffic distribution to multiple paths. In this scenario, the path that is congested, the traffic on that will be reduced by half. Actually, we have established a fluid model to analyze this congestion algorithm, and I'm not going to explain all the details due to the time limitation. We can refer to our paper for details. And according to our simulation results and the fluid model analysis, multipath RDMA can balance the ECN marking ratio among all the sending paths. So that means it can balance the congestion across all the paths. So the second challenge is that how can we track out-of-order packets with small on-chip memory footprint? So speaking of multipath transport, so it will naturally lead to packets out of order. So we need to some metadata to track the out of order. So that is, how can the receiver know which packet has arrived and which packet has not? However, the out of order degree depends on the path latency differences. Normally, the latency, out of order degree is quite small. However, in certain scenarios, the out of order degree can be very big. For example, if we misconfigure one ECN threshold on one of the sending paths, then all the out of order will increase a lot. And another scenario is that when one sending path, the link is downgraded from a high speed to some low speed, so the out of order degree will also increase. And also, because RDMA uses PFC to prevent packet loss, so if one path is PFC paused and then other paths are not, then the out of order can be, say, infinite. So that gives us a second challenge. So how can we track these out of order packets with very small on-chip memory footprint, even if the out of order in certain scenarios is so big? So we adopt an approach called out of order aware path selection. So actually, multipath RDMA will choose its paths with similar delays. So to achieve this goal, the sender maintains 2 pointers. One pointer is called send OOH. So this pointer marks the highest packet sequence number that is successfully received at the receiver. So this actually marks a fast pass. And also it maintains a second pointer called send OOL. This is the smallest ACK PSN that can clock out one packet. And we use a delta parameter to adjust the network out of order degree. So all the packets, all the ACK packets that returned from the network with the PSN within the range of send OOL and send OOH, we target it as a good path. So this ACK can clock out packets to the paths that are returned. And for those ACK with PSN that are lower than the sender OH pointer, then those paths are bad paths. We will eliminate those paths for further transmission. So let's look at an example. So we set the delta to 3 in this example, and first there are 6 packets in the network. However, let's assume that the first pass is a slow pass, and as the fast pass ACK returns, so the sender OH and the sender OL will adjust accordingly, and it falls in the fast pass range, so there will be data transmitted on those paths. However, when the ACK from the slow pass comes to the sender, then its PSN is lower than the sender OL pointer. So this multipath RDMA thinks it is come from the slow pass, so it will drop the ACK and decrease the congestion window. So the slow pass will be eliminated from the further transmission. Actually, we have evaluated this mechanism in our testbed, and while adjust the delta, we can actually control the out-of-order degree in our previously mentioned the 3 scenarios. And also, we can use a delta to control the out-of-order degree, then it will lead to very small out-of-order in network, and it can improve the throughput. If we use a very small bitmap to track the out-of-order, then without the out-of-order control mechanism we mentioned, then the throughput will drop a lot. So with this mechanism, multipath RDMA can track the out-of-order with a very tiny bitmap, even at those very abnormal scenarios. So let's look at the third challenge. So the third challenge is how to provide message ordering without hurting the performance. So actually, because the NIC buffer is so small, so when the out-of-order data arrived at the receiver, we cannot store it in the NIC. So we have to put the out-of-order data directly into the application buffer. So it will lead to a problem. The problem is that some application will assume that all the messages of the RDMA is arrived in order. For example, some application will first send out one message to write some data on the remote receiver, and then issue another write to write the metadata to notify the receiver about the arrival of the first message. And the application will pull on the metadata to check if the data of the message 1 have arrived. And if the out-of-order happens and we directly place the data into the application buffer, then the message 2, the data will already arrived before the message 1 data is ready. Then the application read the wrong data and they run into some error. So one naive solution is to perform stop and wait. So after message 1 send out, we will wait until all the ACKs of message 1 have arrived at the sender, then we will send out message 2. However, this obviously will just downgrade the throughput a lot. So this leads to our third challenge, is how to provide message ordering without hurting the application performance. So we adopt a solution called a Synchronise Mechanism. So multipath RDMA will provide a synchronized interface to the application. So a synchronized message will be guaranteed to arrive after all previous messages. So multipath RDMA will optimistically transmit a synchronized message. So a synchronized message will not wait until all the previous ACKs returns, but will just wait for a small delta t before all the previous messages are sent out. And we set this delta t proportional to the delta we used to control the out-of-order degree in our out-of-order aware path selection. So adopting this mechanism, so we can have very high performance and without, so can ensure the application logic correctness while without the performance degradation. So we also conduct some experiment on our testbed. So there's actually low performance sacrifice for the low messages, and there is a little downgrade for the small messages when the percent of the synchronous message ratio is very high. And all the synchronized mechanism can provide message ordering without sacrificing the throughput. We have implemented the multipath RDMA prototype in our ClickMP FPGA platform. So we use a Altera or Stratis V-D5 FPGA board with two 40 gigabit Ethernet ports. And in total, we write 14 ClickMP elements and 2 K9s of OpenCL code. So in our implementation, our sender logic can achieve a clock frequency of about 200 MHz. And the receive logic also can achieve very high performance. And this prototype actually can send and receive at 9 rate. And the latency is quite low, and the send-receive logic, the latency is all below 1 microsecond. And all the states, because of our previous introduced mechanisms, all the states that we needed for each connection is only 66 bytes. So this means that our multipath RDMA can be implemented in hardware with very high performance. So we have further used 10 FPGA boards and to set up a leaf spine topology, construct 4 equal cost paths. And with the base RTT in our testbed is 16 microseconds. So our key results is that we can improve the throughput compared with the single pass DCQCN by 47%. And also it is very robust to the loss, because it can use the good paths to retransmit the data that is lost on those failed paths. So it can achieve about 3 times throughput improvement. So in summary, this is the first effort to design a multipath transport for RDMA environment. And we use the following techniques to minimize the on-chip memory footprint. So those techniques are, we don't maintain per path states, and we use an out-of-order aware path selection to control the out-of-order degree in the network. And also we use a synchronized mechanism to ensure the message ordering. So with these mechanisms, we can improve the throughput, reduce the latency, and also it is very robust to the failure. So thank you for your attention.
Questions?
Great work. But I just have one question, because I'm also working on kind of RDMA, but I'm using Mellanox NIC. In Mellanox NIC for the RC transport, they will if we got the out-of-order packet, the receiver will silently drop the packet. But it seems in your case, you build your own RDMA protocol on your own board. Is that correct? Because you directly put the out-of-ordering packages content to the application buffer.
Yes. Actually, we can give it comparison between the multipath TCP and the TCP. Multipath TCP will modify a lot on the TCP, right? So it is not an incremental design, just we need to redesign the RDMA NIC.
I see. Okay, yeah. Interesting.
Joe from UW. Really nice work. I really like it. So in your congestion control scheme, when you see an ECM bit, when you see an ACK with an ECM bit mark, you will actually reduce the congestion window by half. You actually reduce it by half a segment,
yes,
rather than actually reduce it by half.
Yes. So
can you just give a sense of why do you design it that way, and how does it impact conversions and fairness?
Okay. So actually, we designed this scenario. We designed this mechanism. Actually, the insight is similar to the DC-TCP. So DC-TCP will react to the congestion. The window reduction is proportional to the ECM marking ratio. So actually, if we reduce one segment for one ECM packet, so actually we are mimic this kind of insight.
Jongnek came from Microsoft. So in RDMA, there are some packet execution ordering requirements. So an earlier RDMA write should be executed earlier than a following RDMA write. So if packets arrive out of order, So how can you deal with this in-order execution requirement for write, not only for send and receive?
Okay, so actually you can adopt the synchronized mechanism. So if you want some messages to, some operations to execute in order, so you just tag some synchronized tags on it. So the transport will ensure that those messages arrived in order at the other side.
Okay, Shahar Reindel from Microsoft as well. You were telling all of that about your implementation. Did you explore working with other RDMA vendors to make it interop? Did you try to push this stuff to something that can work with existing implementations?
Actually, we're discussing we are in discussion with the Microsoft production team. So, but we currently have no solid plan for this. Yes, but for research, I think it's good to push it to the limit. Yes.
Okay, so I also have a question. This is a very nice work, but I have a puzzle in my mind. So I wonder how much this MP-RDMA are really needed in practice, because for example, you have you design this work for like high-speed networking, right? 100G network. So for a single pass RDMA, well-designed single pass RDMA, over 100G network can deliver very good performance with low latency, right? By this, can you name a few applications that we really need multipath RDMA?
Yeah, actually. Okay, so actually, his question is that whether if there are any applications that can really benefit from the
right. So
multipath RDMA.
Multiple 100G paths simultaneously used. Right.
So actually, if you increase the bandwidth in the network, actually the application you adopt will be, I think, will be proportionally increased. The traffic will be proportionally increased.
Right.
So. So actually, the problem we are solving here is that the ECMP caused hash collision. So I think in this scenario, so the problem is still, no matter how the bandwidth has increased, this problem still exists. So I think using multipath RDMA, we can still increase the overall network utilization. And also, more importantly, we can, because currently single pass RDMA, if one pass have one single packet drop, it will conduct some go back and loss recovery. However, in our scenario, we think using multipath to do loss recovery for the RDMA, I think it's very beneficial to the RDMA performance, especially for the application.
Okay, so let's thank the speaker again.